Welcome friends, Igor is here, and in this video we will discover some properties of linearly independent sets. In this lesson we will observe that sometimes it is enough to just glance at a set of vectors to conclude right away that it cannot be linearly independent, and we will find connections between linearly independent sets of vectors and non-singular matrices. Let's get started. Here is a motivational example. Let's look at a set of 7 vectors of size 4. In the previous video, we figured out a procedure how to check if this set is linearly dependent or linearly independent. We have to construct a matrix using these vectors as columns and then look at the number of solutions of the homogeneous system where this matrix is the coefficient matrix. But in this case, we can do better than that. Let's observe that the corresponding homogeneous system is going to have 4 equations and 7 variables. In other words, we have a homogeneous linear system with more variables than equations. But we already know that homogeneous linear systems with more variables than equations automatically have infinitely many solutions. Now, because the homogeneous linear system has infinitely many solutions, this automatically implies that the set of vectors is linearly dependent. There is no need for us to reduce the matrix. We know right away we are going to have infinitely many solutions, and therefore we are going to have non-trivial relations of linear dependence on the set T. Notice that in this example we had 7 vectors of size 4, but of course the important point was that the number of vectors, which is the number of variables in the system, was more than the size of each vector, which was the number of equations in the system. So let's generalize this observation. Suppose you have a set of n vectors of size m. If the number of vectors is greater than the size of each vector, then this set of vectors is automatically linearly dependent. For the proof, let's use the given set of vectors to construct a matrix. The columns of the matrix are the given column vectors. There are n vectors in the set, and therefore this matrix is going to have n columns. Also, each vector has m components, so the matrix has m rows. This is an m by n matrix. Now, if we construct a homogeneous linear system with this matrix A as the coefficient matrix, this system is going to have m equations and n variables. Our assumption says that n is greater than m. In other words, we have more variables than equations, and we know that a homogeneous linear system with more variables than equations always has infinitely many solutions. Because we have infinitely many solutions, we have non-trivial solutions, and each of those non-trivial solutions results in a non-trivial relation of linear dependence on the set of the columns of the matrix. In turn, this means that the set T must be linearly dependent. Now, let's connect the property of linear independence with non-singular matrices. A square matrix is non-singular if and only if its columns form a linearly independent set. This is an if and only if statement, and typically we would have to show 2 separate implications. But sometimes it is possible to prove if and only if statements if the entire chain of argument involves the equivalences, if and only if statements. Let me demonstrate how this is possible in this proof. First, I claim that the statement the square matrix A is non-singular is equivalent to saying that the homogeneous linear system with A as the coefficient matrix has a unique solution. Do you see how this follows? In fact, this is the definition of a non-singular matrix. This gives me an excellent opportunity to discuss one important concept. In fact, all definitions are if and only if statements, even though they are usually stated as if statements, as implications. In fact, they are equivalences, and the reason it is done this way is somewhat strange and pretty much unknown, but that's just the tradition. That's how it is usually done. Keep this in mind. All definitions are in fact if and only if statements, even if they are not stated exactly this way. Now, we know that a square matrix is non-singular if and only if the corresponding homogeneous system has a unique solution. This is the definition of a non-singular matrix. In the previous video, we proved that the columns of a matrix are linearly independent if and only if the corresponding homogeneous linear system has a unique solution. But now, if you look at the beginning and the end of this chain of equivalences, you will see that a square matrix A is non-singular if and only if its columns form a linearly independent set. Now, this was yet another equivalence for a non-singular matrix, and this means our list of equivalent statements for non-singular matrices now grew by one more statement. A square matrix is non-singular if and only if its columns are linearly independent. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see future videos. In the next video in this series, we will discuss properties of linearly dependent sets. I will see you later.